Today my pitch will be about sleep disturbances as markers of neurodegeneration, with a focus on the detection and monitoring of REM sleep behavior disorder, or RBD. So to start off, let's introduce sleep. Sleep is a biological, transitory, and recurrent state opposed to wake, which cyclically alternates between two macro states, which in turn entail two kinds of brain activity, different brain activity. They are the non-REM sleep, which is further divided into three different stages from light to deep, and REM sleep. This latter is also called paradoxical sleep, as it features rapid eye movements and at the same time skeletal muscle atonia. Sleep is really important for human health, as it serves the pivotal function of removing metabolic waste products through the lymphatic system, and this is usually carried out during the deepest stage of sleep. However, this physiological state can somehow be disrupted, for instance in the case of sleep disorders or fragmented sleep, which in turn significantly impair the physiological amyloid beta clearance and therefore lead to an increased risk for neurodegeneration. And for this reason, sleep can be seen as an early marker of neurodegeneration, because the earliest symptoms can be manifest up to 14 years before the diagnosis of neurodegenerative disease. And this represents a growing challenge, also considering the fact that sleep disorders affect up to 70% of the elderly population worldwide, which of course, as we all know, is at higher risk for neurodegeneration and neuro impairment. But taking a closer look on neurodegenerative diseases, we know that apart from being disabling diseases that worsen the quality of life, they represent also a dramatic social burden. Indeed, the estimated annual healthcare cost for Parkinson's disease is around 3 billion euros in Italy, and this cost rises up to $655 billion in the US for Parkinson alone. And this is significant considering the fact that over 10 million people worldwide are affected by Parkinson disease. And about 40% of people with Parkinson also present with REM sleep behavior disorder, either in its idiopathic or in its secondary phenotype. But let's go deeper into details about what is REM sleep behavior disorder. It is REM parasomnia that is characterized by the loss of physiological REM atonia. Therefore, the subjects that are affected by these disorders usually act out their dreams, meaning that they usually manifest violent limb movements or also violent behavior during the night. And this parasomnia also plays a significant role in the pathogenesis of neurodegeneration, as it features a really high conversion rate to alpha-synucleinopathy, which is a family of neurodegenerative diseases, with Parkinson's disease, here represented with the solid red line, being the most common and also the most likely one, with over 90% conversion rate. So it is really crucial to effectively diagnose sleep disorders and properly monitor also the disease progress in order to improve the quality of life of patients. But sleep disorders frequently remain undiagnosed or untreated. But why? Well, let's take a step back. The gold standard to assess sleep disorders is polysomnography, which is an exam that is performed during sleep and involves recording biosignal from a high number of recording electrodes, and it is usually performed in a sleep laboratory. However, this exam is highly impractical, as the recordings are then manually scored by a sleep technologist, and we're talking about 7 or 8 hours of recording, so it's really a cumbersome process. And this exam is also regarded as invasive by the subjects who undertake it, because they are forced to sleep not only in an unfamiliar environment, but also with a lot of cumbersome instrumentation. So, as previously stated, REM sleep behavior disorder represents an entry point to alpha-synucleinopathy, but at the same time, given that the neurodegeneration process is thought to be a gradual one, it offers a window for disease-modifying intervention. Therefore, there is the need for early and fast diagnosis before overcoming the polysomnographic process to effectively catch the onset of the neurodegeneration, but also the need for personalized follow-up procedures in order to properly monitor and manage the disease and therefore improving the quality of life. So today's speech will present a framework for the automatic detection of REM sleep without atonia and also the assessment of the disease progression. So how is RBD assessed today? Well, the state-of-the-art methods to assess RBD rely primarily on clinical interviews and manually scored metrics, which, however, are visual and threshold-based, meaning that they are really prone to inter-rater variability, but also intra-rater variability. And an automatic index was also proposed, which may serve as a fast-line method for revealing REM sleep without atonia. However, it is threshold-based, so it is easily prone to artifacts such as crosstalk from other muscles or muscle activity, which may happen during REM sleep. So the aim of this work was to implement a spectral analysis of electromyographic or EMG segments in order to overcome the inter-rater and intra-rater variability and provide an objective measure to quantify REM sleep without atonia. So as regards the pre-processing of the EMG signal, which was recorded during REM sleep only, we performed a bandpass filtering from 10 to 100 Hz as per the international guidelines on REM sleep without atonia scoring. Then we framed the signal to 1 second epochs to match the current automatic methods. Then the power spectral density was estimated through the Welch periodogram in order to evaluate also the frequency distribution of the signal over the spectrum. And finally, we performed the feature extraction, focusing on, of course, the spectral parameters that characterize the signal. But taking a closer look at real-world data, we have in this plot the EMG recordings from the submental muscle for a healthy subject and for a subject suffering from RBD. So, as appreciable, these two recordings feature a very different submental EMG pattern. So, in particular, the recording of the RBD subject features an increased and sustained EMG activity, which of course is not physiological, because as previously stated, during REM sleep we normally feature muscle atonia. And also from a spectral perspective, meaning a frequency-based perspective, which was the one adopted in this work, the EMG activations during REM sleep differ into populations. So this means that the extractive features well characterize the two groups. So to perform the automatic detection of RBD subjects in our study group, the EMG features were analyzed along with the clinical variables derived from the polysomnography, which describe, for example, sleep quality or sleep fragmentation, and were employed in supervised machine learning models, which are models that are able to learn from data and then are able to detect significant patterns in when presented with new data. So the extracted parameters from the electromyographic features proved efficient in detecting RBD, showing 93% sensitivity with an 87% overall accuracy, and also over an 87% precision, meaning also protection against false positive. And external validation was also performed on unseen data recorded at the sleep disorder centers at Politecnico hospital in Turin. and no significant performance deterioration was observed when switching from the cross-validation to the external test set, thus meaning that that's ensuring a good generalization capability of the provided and the developed model. But as previously said, REM sleep behavior disorder offer a window for early interventions, and the neurodegeneration process is thought to be a gradual one. So the automatic detection of RBD subject, of course, is okay, but it's not enough. And there is the need to effectively monitor the disease progression. So the idea behind this work was to design a continuous score correlated with the degree of REM dissociation. That means the extent of REM sleep without atonia. However, there is no clinically validated disease model. So this work proposed a framework for assessing each subject's similarity to a healthy model through distance-based metrics. To do so, a search neighborhood was first defined, and it was defined exploiting the interclass dissimilarity in terms of the Euclidean distance between 2 points in space, which virtually correspond to the healthy subjects and the RBD groups. Then, a healthy model is inferred from the healthy subject data and is treated as a feature array and then considered as a healthy reference. Finally, a range search approach was applied in order to detect the RBD subjects inside the neighborhood and then compute their distance from the reference healthy model. So, to the purpose of this work, the Euclidean distance works as a similarity measure, where the higher the value, the larger the difference from the reference model, also suggesting a higher impairment or a higher dissociation. Then the obtained distance values were mapped to an index in order to gain a continuous score which not only was normalized but also independent and reproducible. And this score is called the dissociation index, which virtually describes the degree of REM dissociation, therefore REM sleep without atonia impairment. And this index was tested on both healthy subjects from another cohort and RBD subjects. And as appreciable, the healthy subjects, here represented in orange, feature lower values, implying stronger similarity to the healthy reference, whereas increasing values of the dissociation index suggest a higher degree of the impairment, therefore higher distance from the healthy provided model. But how can this index be put into practice, for example, for personalized follow-up procedures? Well, after computing the dissociation index value for each subject, 4 disease progression tiers were identified by exploiting the statistics on the available data. And after that, each subject was located into the corresponding disease progression tier or impairment tier. And this is really important because the physician, while monitoring the index value, could also evaluate the disease progression over time, and this allows for easier follow-up procedures or also easier longitudinal evaluations. So to sum up, the identified spectral features in this study proved efficient in detecting the RBD subjects from the healthy ones, therefore overcoming the threshold-based metrics which are prone to muscle artifact, to inter and intra-rater variability. And moreover, the proposed dissociation index effectively discriminates the healthy and RBD class, as we could observe from the provided box plot. And its variability inside the RBD class is also useful for follow-up and longitudinal evaluation, as we have seen. And these findings also serve as a feasibility assessment for lightweight detection and lightweight monitoring of RBD, therefore requiring fewer data, fewer electrodes applied to the subjects, and also lower computational time. And where to next? Well, the next step is sure to go beyond the mere diagnosis of RBD. In fact, it is really important to exploit the diversified nature of REM sleep with allotonia before its conversion to alpha-synucleinopathy. And to do so, it is really important to go deeper into detail in the transition zones to understand the transition process from a healthy or low-risk tier to a moderate one. And finally, the last step is to enhance the robustness of the index by validating it on a larger cohort, comprising also different alpha-synucleinopathies such as dementia or dementia with Lewy bodies and multiple system atrophy, apart from Parkinson's disease. And this is all for today's speech. Thank you all for the attention. If there are any questions, I'm happy to answer, or here you'll find my contact information if you have any later. Okay, thank you.